My name is Baker Lee, and I'm from Beijing Institute of Mathematical Science and Applications. The title of my talk is Cryptanalysis of the SNOVA signature scheme. This work is joined with Dingjing Tai. Okay, last talk helped us familiar with UOA scheme, but I just want to recall the structure of UOA because SNOVA is a UOA type scheme. SNOVA is a multivariate signature scheme based on UOA scheme submitted to the additional NIST PQC standardization project started in 2022. It has lower public key size compared to UOA. This is why we are interested in it. First, we will recall the UOA structure. UOA scheme is based on the trapdoor multivariate quadratic function. We know how to use trapdoor function to construct a signature scheme. Next, I will introduce how to construct such trapdoor function. First, the central map is designed such each polynomial is quadratic of the following form. We notice that the matrix is special. The row right block is 0 with size m times 2n. So first variables are called vinegar variables. The last variables are called oil variables. Just look like vinegar and oil will separated. This system is easy to find pre-image. If we fix the vinegar variables, then the above system will become a linear system. This is important for us to have to find a pre-image. Next, a linear map as is then randomly chosen next to the public key map is just a composite f and s. The secret key is s. The function of s is just to help us to hide the structure of the central map. In general, it's hard to find a pre-image of P unless we know a basis of the OU space, or where O is defined by the inverse of this special space. Notice that the P action on O is will map to 0. Okay. Your way has an advantage. It has short signature and short execution time, but its disadvantage is that it has larger public key size. This is the following table shows us your way has large public key size than the result, but SNOVA has small public key size. The idea of SNOVA is replacing the coefficients ring FQ by matrix ring to reduce the size of public key. Next, I will describe the SNOVA scheme. First, R is a L times L matrix over FQ. In general, according to the parameters submitted by SNOVA teams, L equals 2, 3, 4. Here, PF with bracket denote some n times m n matrix whose entries are elements of R. R is a matrix. For each Q belongs to R, we use lambda Q to denote the n times n block matrix whose diagonal elements are Q. Next, we will define a special subring, FQS. FQS is a polynomial ring generated by S. S is an L times L symmetric matrix randomly chosen from R. And the characteristic polynomial of S is irreducible. This condition is necessary because if the characteristic polynomial of S is reducible, then the scheme SNOVA scheme will not save. Notice that FQS is a subfield of R and the dimension of FQ is L. Next, just like your way structure, we first construct the central map. Fi equals such complex system, but the matrix Fi in the center is a foreign form, just look like your way. But each entry of such matrix belongs to the matrix R. And A alpha, B alpha are chosen randomly from R. And Q alpha 1 and Q alpha 2 are chosen randomly from the special space FQS. We want Q alpha 1 and Q alpha 2 are invertible. So, and I want to say that the A alpha and B alpha is necessary here, because if we move such A alpha, B alpha, and Q alpha 1, we just move it. Then for some elements in Rm, we can find some pre-image easily. This is why we need A alpha, B alpha, just avoid some forgery attack. Now we want found a invertible linear map T to hide the structure of the central map F. T is a map set corresponding to the matrix in this form, but each entry of the matrix belongs to the FQS. Okay. Then actually this structure is as same as your way. Let P equals F composite with T, set xt times U. Then Pi will equal this form, just calculated by Fi and T. Now the public key of SNOVA is P, and A alpha, B alpha, Q alpha 1, and Q alpha 2. And its private key is F and T. Actually, maybe T is enough, because if we use T and public key, we can calculate the central map Fi. Now the signature is very, to sign a signature is very easy. We just choose random values A1 to AV belongs to R as Winiger variables. Then the system, just as a system associated the central map, will become a linear system with L square M equations and L square M variables. Since on the left, on the right side, each position will provide L square equations, and on the left side, each variables xi where I bigger than v will provide L square variables. So the signature equals the inverse image of T. Verification is very easy. Just use the public key to check that hash message equal P signature. Okay. The advantage of SNOVA, I have said to use that it has more public key size than your way scheme and division. Now I will introduce the structure of SNOVA. The first claim is that SNOVA with parameter VMQL scheme can be regarded as your way L times V L times M Q scheme with L square M equations over FQ, rather than L square with your way scheme over FQ as claimed by the authors. This is the claim. This claim is the most important because complexity given by SNOVA team is just to use their claim. They think SNOVA is equivalent with your way L square V L square M Q scheme. But if SNOVA is regarded as your way L V L M Q scheme with L square M equations over FQ, then the complexity will become smaller. Okay, I will explain to you why we can do this. All the metrics FIT, PI can be viewed as Ln times Ln matrix in the big matrix string. We notice that the lower right Lm times Lm block is 0 block for each Fi. Therefore, there exists a common Euler space of Fi over Fq with dimension L times m. If we set O1 is this vector space, then the inverse image of O1 is the Euler space. Note that for any U V belongs to O, we have the following equations. So if we solve these following equations, well, we can find the Euler space of the SNOVA scheme, and the Euler space can help us to find the preview image. Actually, there we have another claim. SNOVA scheme can induce a standard UV scheme. Here, the meaning of standard UV scheme means that the dimension of Euler space equals the number of equations. But such UV scheme is over the extension field. We can recover the Euler space of SNOVA by recovering the Euler space of the induced UV scheme over the extension field. But we are not going to use the induced UV scheme to give specific complexity of SNOVA scheme, since such complexity is still large. If we have other method to find this Euler space of induced UV scheme, then maybe we can reduce the complexity of SNOVA, but I don't know. I just explain to you how to do this. Let lambda be an eigenvalue of S, and Kc is an eigenvector corresponding to lambda. Just take O2 is this form, then for any U V belongs to O2, we have this formula, because each entry of, okay, sorry. Yeah, because Kc is a common eigenvectors of Sg and Sk. Then we just restrict the SNOVA on the FQLn. Then we can calculate its public key, and the Euler space is just defined by O2 prime. And this is a new UV scheme. In following, we only use the claim 1 to give the new complexity of SNOVA. Claim 1 says that SNOVA scheme can be regarded as a UV scheme with a dimension of Euler space only L times O over FQ. Okay. Next, we only consider the key recover attack. The Kibernese-Shamir attack is the complexity given by this formula. The following is not maybe not very important because the most important is the first claim. And the reconciliation attack says that we just found, if we found an element U belongs to the Euler space, then we use equations, the following equations. We get many linear equations, and so the most difficult step is the first step, is that how to find an found an element belongs to Euler space. Because the parameter given by SNOVA there are many variables. L will always bigger than the number of equations. So there are many solutions of 3.1. It's not all your element. So we need to try one by one. If we found a solution, we just try to test is it all your element. The intersection attack is that if let M1 and M2 be two invertible matrices in the set of linear combinations of the systems, we just want to find an element belong to the intersection. If 2Lm bigger than Lv, then such element will exist. We just need to solve this function or this system. Otherwise, if L2 times L times M smaller than Lv, maybe such intersection may have no non-trivial vector. So the complexity will given by this. Okay. This table is classical complexity of by using our attack. Actually, SNOVA and we use the same attack, but just use different claim. So in each pair, the right is a complexity given by SNOVA, and the left is given by us. We know that the the complexity on the left is smaller, is much smaller than right. And in the case of L equals 2, some parameter will not reach the security level of NIST. Okay, later the team of SNOVA submitted new parameters for L equals 2 and modified their complexity. So, but I have no idea to give new attack to SNOVA. Thank you for listening.
One question. And so following your attack, so they propose new parameters, and so it's still competitive?
Yeah.
No more questions. Thank the speaker.
Thank you.